Welcome to Statics.
Simplification of a force and couple moment system. When analyzing a system of forces and moments, it is sometimes convenient to simplify the system by finding the resultants of the forces and moments acting at a single point. What we want to create is a simpler but equivalent system that produces the same external effects on a body. By external effects, I mean cause the body to translate or rotate with the same direction and magnitude. Or for static problems, cause the same resistance to translation and rotation at the supports. When creating an equivalent system, there are a few rules you should keep in mind. Let's look at case 1, where we have a force that we want to reposition to a point on its line of action. In this example, we have a force acting at point A, and a second point O lies on the line of action of the force. We want to slide the force from point A to point O. We can think of this graphically as adding two forces at point O that are equal and opposite along the line of action. The outermost opposing forces cancel each other out, and we are left with the force F that has been moved from point A to point O. This property is referred to as the principle of transmissibility, which is that the external effects on a rigid body remain unchanged when a force acting at a given point on the body is applied to another point lying on the line of action of the force. Note that the internal effects may change, but that is not our concern right now. We'll look at internal effects and the stresses they cause in a future Mechanics of Materials course. Here's another example that you may be able to relate to. Suppose I tie a cord around your wrist and pull it as shown. Then suppose I move the cord location to above your elbow and pull with the same force and direction. The pull on your shoulder will be essentially the same. In the second case, we want to move a force from one point on a body to another point that is not on the line of action of the force. In this example, we have a force applied at point A. I would like to get an equivalent system by moving the force to point O instead, which does not lie on the line of action of the force. Again, we can think of this graphically as adding two forces at point O that are equal and opposite, and in the direction of the line of action of the force. In this case, we see that doing so forms a force couple. The vector R is a position vector between the lines of action of the forces in the couple. If we take that couple and simplify it to a moment, we are left with the force now moved to point O and a moment defined by R cross F. We refer to this moment, whose axis direction is pointing straight out of the screen in this example, as a free vector because it is a pure rotation. We can move it to point O or A or some other arbitrary point. In summary, when we move a force to another location not on the line of action, we introduce a couple moment or a tendency to rotate. Here's another example that you may be able to relate to. Suppose that you hold a load at arm's distance as shown. That load not only pulls downward on your shoulder, but also tends to cause rotation of your arm at your shoulder. When you move the load over to your shoulder, the force still pulls downward on the shoulder. However, the rotation is no longer felt. To get an equivalent system, a moment would also need to be applied. This final case is about moving moments from one point on a body to another. As I mentioned a minute ago, because the moment is a pure rotation, it can be moved to any place on the body and have the same effect. Now let's look at the approach for finding an equivalent system for multiple forces and moments acting on a body simultaneously. The approach will be to find the resultant forces and moments. In other words, if I have several forces and moments on a body, I will combine them to simplify the whole system. Generally, I can reduce them to a single force and a single moment. This will make it easier to understand what is happening to the body. So for two-dimensional problems, we will be summing the forces in the x and y direction and summing the moments about some particular point. For three-dimensional problems, we will do the same thing, sum forces and sum moments, except we will use vector notation.